So now that we've gained a little bit of insight about this concept of the binding energy per nucleon, let's take a look at a graph of what the various different atomic nuclei that exist in the universe look like if we graph them all together. Now we start off by looking at the binding energy per nucleon, and this is in terms of MeV. Remember the previous examples we found all were essentially between approximately 7.1 and about 7.8 or so. So if you look at the beginning of the curve, of course at the very beginning there is no binding energy per nucleon because hydrogen 1 is not bound to any other nuclei. So it has a binding energy of 0. As we bind it, we find that there are several variations in which the binding energy is actually increasing, but the binding energy is still pretty low. These guys down here are not very stable because all atomic nuclei would like to achieve the highest possible binding energy per nucleon. The higher the binding energy, the more tightly bound they are and the harder it is to break them down or to separate them into their individual constituents. So while these are bound and have a fairly significant binding energy per nucleon, they're still relatively low. You can see that if you look at this curve that we would find an average value somewhere just a little bit under 8 or so. So as we move up the curve, we find here was our first one, helium. This guy had a binding energy of approximately 7.1, 7.2, somewhere around there. You can see that after going from helium, the binding energy per nucleon actually drops dramatically. And we move down to several versions of lithium, then beryllium, and then boron. We don't actually achieve a more tightly bound nucleus, that is to say, a higher binding energy per nucleon, until we reach carbon. So ultimately what happens in stars is when they are fusing the lightweight elements to make the heavier elements, they tend to skip over this portion and they go straight from helium to carbon. As you might imagine, if I combine 3 helium nuclei together, I can produce 1 carbon nucleus. And so we tend to find that these nuclei are in much lower quantities because the stars simply skip over them because these are less stable nuclei. Now you can see the line sort of zigzags back and forth, but you can see the guys who are stable. Carbon is stable. Oxygen is stable. We move up a little bit when we move to neon. Remember, neon was an important one. This is about the point at which we start having more nucleon, or more neutrons, I should say, than protons. That was around atomic element number 19 or 20. So these are very important elements. We continue to move higher and higher along the curve, achieving slightly more. We've actually passed 8 as we pass oxygen and head into neon. We've actually passed 9 MeVs per nucleon, and we find that the peak is right here with atomic number 26, iron. And this has a mass number of about 56. 56 nucleons. 56 nuclear particles produces the most tightly bound nucleus of all atoms. Once we go past this point, we actually find that we're slowly sliding down the curve. We're actually decreasing the stability of the nucleus as we make bigger atoms. And so this sort of explains why we're able to get energy by going both in the forward direction, by fusing together smaller nuclei to make heavier nuclei, but then also going in the opposite direction, where we have radioactive decay and nuclear fission, where we take a big element or a big atomic nuclei and we break it into smaller ones. Everybody is trying to move in this direction towards the highest part of the peak, and the highest part of the peak is right up here at just slightly under 9 MeVs per nucleon, and that's the peak at about iron. Now you can see on either side of iron is not an enormous difference, but iron is the most stable atomic nuclei. It is the most tightly bound and the hardest atomic nuclei to break apart into its constituent parts. We found that gold, remember gold would be somewhere down here around this point, just slightly under 8, still pretty stable, but definitely not as stable as iron. Iron takes approximately 1 MeV more per nucleon than it takes for gold to be broken apart. So this curve helps us to understand why we have nuclear fission on one side. Nuclear fission is the breaking apart of big nuclei to move towards this stable atomic nuclei, iron. And then we have fusion on the other side, where we fuse together smaller atomic nuclei to produce more stable nuclei, ultimately ending with this iron. So let's take a look at some of the different decay processes, and then let's talk about the fusion side of the binding curve and then the fission side of the binding curve.